Hello, I'm Michael Miljanovich, and this is an introduction to structural induction. Let's start out with a problem. Suppose we need to show with induction that if T is a full binary tree, then the number of nodes in that tree is less than or equal to 2 raised to the power of h of t plus 1 minus 1, where here h of t is the height of the tree. How are we going to do this? So what does a full binary tree look like? A full binary tree is any tree where every node either has two children or is a leaf. So the simplest one of these would just be a single node. If we wanted to build things up another step further, we could have a single node with two children, and those two children, which themselves are full binary trees, are just leaves in this case. In essence, any full binary tree that we want to have can simply be built by taking any root node and adding to each of the two sides, left and right, a full binary tree. So we can take this tree that we have here and put that on the left side, and we can put something maybe even a little bit bigger on the right side. So here's another full binary tree. And you can see that at every level, all of the nodes either are going to have two children or are leaves themselves, and these are all full binary trees. Now, if we want to solve this problem with induction of finding out the number of nodes with respect to the height, we have a bit of a problem if we're just going to use simple or strong induction. Namely, simple and strong induction only really work for predicates when x, the thing that we're putting in the predicate, is a natural number. So if we're looking at the predicate of 0, predicate 1, and so on and so forth. But what happens if it's not? What happens if we have a formula, or we have a list, or in this case, we have a tree? These induction techniques just aren't going to do what we need them to do. So this is where we use structural induction. The idea behind structural induction is that it works for any recursively defined set. In other words, for any set where there is one or more base case elements, so in this case we have just a single node, and to make larger other elements of that set, you need to follow rules that generate them based on existing elements. So in the case of our full binary trees, well, the base case is just we have a single node, and if we want to make the next largest one, we need to use a rule to go from that to the next biggest tree. The whole purpose of structural induction is that it's a technique that proves every element in a set has a property. So in this case, every tree is going to have a number of nodes that relates to the height of that tree. If you're going to do something different, such as looking at whether every element that has a property is in that set, for example, every tree that has X amount of nodes is in the set of full binary trees, you should be using the other kinds of induction, simple or complete induction for that. Before we go to our full binary tree example, let's look at something really, really simple. Consider a set where all we have is the letter A, it belongs in the set, and in addition to that, for any other elements of the set, that element surrounded by a pair of parentheses is also in that set. So we can have A with a pair of parentheses, A with two parentheses on the left, two parentheses on the right, and so on and so forth. And now let's suppose we need to prove that all elements of that set have an equal number of left and right parentheses. This seems kind of obvious because you're always adding one to each side. So if we're going to prove it, well, in the base case, we have A. It has 0 left and 0 right parentheses, so that holds true for the base case. And then for our reduction step, suppose that x is in the set, then x is going to have n left parentheses and n right parentheses for some number n, and they're equal, which means that if we're going to build the next largest element of that set, we need to add one more to the left and one more to the right. So the next element, x with the parentheses, has n plus 1 and n plus 1, which are both equal. Awesome. So let's go back to our problem. We want to show that for any full binary tree T, so that's T is in the set of full binary trees, the number of nodes is less than or equal to this formula, 2 to the power of the height of the tree plus 1, all minus 1. And remembering that h of t is the height of the tree. Let's take a look at how we build a full binary tree. So the very simplest we can have, other than the empty ones, we'll ignore the empty ones for this problem, is just the single node R. Every other tree that's non-empty is formed by taking a new root node R and adding two trees to either side, T1 and T2. So in the really simple example we had before, we had our root node, and then we just added two new root nodes left and right. But we can also build bigger ones like we saw earlier. Let's go through a few examples of what these might look like. So here's our really simple base case node R. It has a height of 0. So height is going to be defined here as the distance between the root and the lowest leaf. So since there's the root and the leaf here are the same, there's really no height, there's no distance there. Let's suppose our next simplest example. We have a root node with 2 trees on either side, and those trees are just each a single node. So the distance between the root node and the leaf here is just 1. There's only one step to go through. Let's look at our bigger tree from before. We have our root node. On the left side we have this tree, and on the right side we have this tree. So the height of this whole thing is 3. If you wanted to count how many steps it took you to get from the top to the bottom, well, from our root, we can go from here to here to here to here, and that's 3 steps that we took to get it, so it's got a height of 3. And remember, we're counting from the root to the lowest leaf, because if we went the other way, that would only be height 2, but that's not the height of our tree. So let's define the height of a full binary tree. In the base case, we just have a tree that's a single node R with a height of 0. And that kind of makes sense. Now we're going to do a recursive step where we look at any 2 full binary trees, T1 and T2, that already exist. And if we combine those trees to make a larger one with a new root node R, then the new height is going to be 1 plus the maximum of the height of those 2 trees. So let's say we have T1, which is this tree over here. We have T2, which is this tree here. Now this is a single node, but that's still a full binary tree. All of the nodes either have 2 children or are a leaf. Now the height of the tree on the left is a height of 1. The height of the tree on the right is a height of 0. So if we add a new root node R, the maximum of 1 and 0 is 1. And so 1 plus 1 gives us our new height of 2. Now how about how many nodes are in a full binary tree? Well, once again, pretty simply in our base case, the tree that's just node R has a single node. Look, there it is, 1. Now, how about recursively? Suppose we have our existing full binary trees, T1 and T2, and if we combine these with a new root node R, the number of nodes is 1 plus the number of nodes in the left tree plus the number of nodes in the right tree. So this is pretty simple. If we have our tree from before, T1, T2, T1 has 3 nodes, T2 has 1 node, and if we add our new root node R, then we have a total of 1 plus 3 plus 1 is 5. Now let's get started on our proof. So in our base case, we want to show that the proof holds for the very simplest case, so it holds for a single node. If that works, then we can actually apply our structural induction. In our induction step, we're going to show that if the proof holds for T1 and T2, then it is true for whatever the next largest tree is. So for instance, in this case, we take our T1, our T2, we add a new root node. That means we've, by definition, made a bigger tree. And so by induction, this is going to apply to all of the full binary trees that we're working with. All right, so let's do the proof. So remember, this is what we're trying to prove. If T is a full binary tree, the number of nodes in the tree is less than or equal to this formula. So let's look at our base case. In our base case, T is a full binary tree and it's just got 1 node, that root node R. So the height of that tree is 0. We defined that from before. And so if we plug that into our formula, so we have then 2 to the power of 0, because the height of that tree is 0, plus 1 minus 1. Well, that means it's 2 to the 1, so that's 2, minus 1, which is 1, and that is less than or equal to 1. Sweet, we've got it done. So that was the simple part. Now let's move on a little bit to the next step where we're going to do our induction. So now we'll suppose T1 and T2 are existing full binary trees, and suppose that our induction hypothesis holds for each of those. That is, the number of nodes in each of those trees is less than or equal to this little formula for each of those trees. We'll also suppose that T, the new one that we're trying to build, is the combination of T1 and T2 with our 1 additional root node R. So let's go through our proof step by step and see what we can show. First off, by definition, the number of nodes in our tree is 1 plus the number of nodes in the left tree plus the number of nodes in the right tree. The height of our tree is 1 plus the maximum height of either the left side or the right side. Whichever tree is bigger, we take that height, we add 1, that's the height of our new tree. Now, by our induction hypothesis, the number of nodes in our tree, which is 1 plus the number of nodes in T1, number of nodes in T2, must be less than or equal to 1 plus, and now we can substitute the, using the induction hypothesis, the number of nodes in T1 with the formula that we have from before, namely 2 raised to the power of the height plus 1, all subtract 1 for each of these. Doing some arithmetic, we can cancel out the -1 and the +1, and what we're left with is these two terms, 2 raised to the power of each respective height plus 1, each again, and then with just one -1 left. Now the sum of these must be less than or equal to the larger of them doubled. So that means we have this is less than or equal to double the maximum of these two terms minus 1. We also can see that in common between these two terms is the base 2 raised to these powers. So if we take the 2 out of this maximum term, we end up with 2 times 2 raised to the power of the maximum of either height of the tree plus 1 or height of the tree plus 2. And we also can take the +1 out of either side because, once again, we're just looking at which is bigger, the height of the first tree or the height of the second tree. We can add the 1 afterwards. Now, if you are really careful, you can notice that this term we have here, the maximum of the height of the first tree or the height of the second tree plus 1, is this definition that we have over here, namely the height of our tree that we're currently working with. So we substitute that in using our definition, and now we have 2 times 2 raised to the power of the height of our current tree minus 1. And so since the base of these two are the same, we can change that into 2 to the power of the height of the tree plus 1 minus 1, which is what we wanted to show with our proof. So hopefully that was a good example of structural induction, and hopefully it was useful to you. Look forward to you guys looking at my videos in the future. Thanks for watching.